All right, so everyone in finance talks about risk, right? But what does that even mean? A lot of the time, it just feels like this abstract gut feeling. Well, today, we're going to change that. We are going to make risk concrete. We're going to use the powerful tools of statistics to slap a hard number on it, turning it from just a feeling into something you can actually measure and manage.
So let's just dive right in head first. How do you actually put a number on the risk of something big, like a 20% market drop? I mean, is it just a guess, a gut feeling? Or can we be way more scientific about it? You bet we can. And that's exactly what we're going to break down right now.
Okay, first things first, we got to understand the type of data we're working with here. On one hand, you've got discrete outcomes. Think of these as countable, separate things, like how many companies in your portfolio might default on their loans. You can have 1, 2, or 3 defaults, but you can't have 1.5, right? It's like rolling dice. You get a specific number. But financial markets, oh, they're a whole different beast. They're continuous. Think about a stock price. Between any two prices, there are literally infinite other possibilities. It's not like rolling dice at all. It's much more like a constantly flowing river.
So, how do we even begin to analyze this flowing river of data? Well, you need the right tools. And our first, most fundamental tool is something called the cumulative distribution function. You'll see it called the CDF. Let's unpack what that is.
So, what on earth is a CDF? Okay, the textbook definition says it's the probability that a random variable, let's call it big Y, takes on a value less than or equal to some specific number, little y. But in plain English, it's just a running total. That's it. It's the total accumulated probability you've seen up to a certain point.
And that's what makes it so powerful and honestly pretty intuitive. Just think of it as a cumulative story. At any point you pick, the CDF just answers one simple question. How much probability have we gathered so far? That's the whole game.
Now, any function that wants to be a CDF has to follow 3 basic rules. Think of them as the laws of probability physics. First, it's non-decreasing. As you move from left to right, the probability can't suddenly drop. It can only go up or stay flat. Makes sense, right? Second, way out at negative infinity, the probability is 0. I mean, nothing could have happened yet. And third, if you go all the way out to positive infinity, the probability has to be 1 or 100% because you've now accounted for every possible thing that could happen.
Okay, so the CDF gives us the running total. But what if we want to know where the action is? Where outcomes most likely to be clustered? For that, we need our next tool, the probability density function, or PDF. This thing gives us the shape of the probability.
All right, time for a little bit of calculus, but don't freak out. It's actually super intuitive. The PDF is simply the derivative of the CDF. All that means is it tells you the speed or the rate at which probability is piling up. So if the PDF is really high in one spot, it means probability is accumulating super fast right there, which tells you that outcomes in that little area are much more likely. Okay, now this is absolutely crucial, so listen up. The value you see on a PDF is not a probability. I'm going to say that again. It is not a probability. It's a density. It's one of the most common mistakes people make. The best way to think about it is like population density. A high number doesn't mean a high probability of picking one person. It just means that area is really crowded. Same thing here. A high PDF value means that neighborhood of outcomes is very, very crowded with likelihood.
And just like the CDF had its rules, the PDF has one big non-negotiable rule. The total area under the entire curve has to equal 1. Always. No exceptions. And that makes perfect sense, right? It's just saying that the total probability of something happening, anything at all within the realm of possibility, is 100%.
All right, enough with the theory. Let's get our hands dirty and actually see how this stuff works with a real calculation.
Okay, here's a classic problem you'll definitely see. Let's say we're given a function, f of y equals c times y squared. And this function only exists on the interval from 0 to 2. It's 0 everywhere else. So the puzzle is, what value does that little constant c have to be to make this a real, valid PDF?
So how do we solve this? We just go back to that one big rule we just learned. The total area under the curve must be 1. So we set up an integral for our function, c times y squared. And since it only exists from 0 to 2, that's our boundary. We calculate that integral, and then we just force the answer to equal 1. That'll leave us with a simple little equation where c is the only thing we don't know.
And when you run the numbers, boom, you find that c has to be 3 over 8. That is the magic number. It's the only value for C that perfectly scales our function so the total area under it is exactly 1, which means we now have a legit PDF to work with.
Okay, before we go any further, there's another mind-bending but super important point we need to lock down. For continuous variables, the probability of hitting one single exact point is 0. It's basically impossible. Think of it like this. What are the odds of throwing a dart and hitting one specific, infinitely small atom on the dartboard? It's 0. There are just too many possibilities. Probability, for us, only really exists over an interval, a range of values.
So if we can't ask about a single point, let's ask a question that we can answer. Using the PDF we just figured out, what's the probability that our variable y lands somewhere between 1 and 2? Now that is a question we can tackle.
And the process is exactly the same. We're just finding the area under the curve again. But this time, instead of integrating from 0 to 2, we just integrate over the little slice we care about, from 1 to 2. And when we do that, we get 7/8, which is 87.5%. See? That's the power of the PDF. It lets us slice and dice and find the probability for any range of outcomes we can imagine.
Okay, this is it. We've built our toolkit, we have the CDF, we have the PDF. Now, let's bring it all home and finally answer that big question about financial risk we started with. To do that, we just need one last piece of the puzzle: quantiles.
So what's a quantile? The easiest way to think about it is that it's the CDF in reverse. The CDF takes a value and gives you a probability. A quantile does the opposite. You give it a probability and it gives you back the value. So for example, the 5th percentile is the value on the map where exactly 5% of all the data falls below it. We're finding the location for a given probability.
And this, right here, is where it gets incredibly practical for finance. The 50th percentile? Sure, that's the median, the middle of the road. But the real action is out in the tails. The 5th percentile? That's how we calculate a super common risk measure called value at risk, or VAR. It basically answers the question, what's a loss so bad we'd only expect to see it on the worst 5% of days? And the 1st percentile? That's for the really scary stuff, the true stress test scenarios.
Theory is one thing, but let's see how this plays out with real-world, messy market data. We're going to take everything we've learned and apply it directly to the daily returns of the S&P 500.
And the data we're looking at covers a pretty wild ride, from the beginning of 2020 all the way through October 2024. I mean, think about everything that happened in those years. This is definitely not a boring data set. And check this out. Here are the numbers. The median daily return, right in the middle, is just slightly positive, which is what you'd expect. But look over at the left tail. That's where the risk lives. The 5th percentile shows a daily loss of 1.91%. And the 1st percentile, the really bad days, shows a loss of almost 3.7%. These are the numbers that tell a risk manager what they're up against.
So let's translate that 5th percentile number into plain English. It means that based on the history we looked at, on any given day, there's a 5% chance of losing more than 1.91%. And there it is. That's the answer. We did it. We took this vague, scary idea of risk and we pinned a number to it. This right here is the cornerstone of how modern finance thinks about and quantifies risk.
So, there you have it. We've used this amazing statistical toolkit to look back at history and put a precise number on risk. It's an incredibly powerful way to understand what has happened, but it leaves us with the biggest, trickiest question in all of finance. Just because we have a perfect map of the past, does that mean we can use it to predict the future?